Hey folks, welcome to Innovate at Edge with Arc-enabled Kubernetes. I'm Anirudh, a product manager at the Arc Kubernetes team with over 5 years of experience across DevOps, containers, public clouds, and hybrid cloud technologies. I hope you find this demo interactive and we look forward to hearing from you.
Hello, folks. I'm Omkar Kulkarni. I'm also a product manager at Arc Enabled Kubernetes with over 5 years of experience across cloud native technologies, DevOps, and solution architecture for both public and hybrid cloud. We look forward to having an engaging session with you.
Welcome to this presentation. I'm Anirudh, a PM at the Arc-enabled Kubernetes team. Today, I'll give you an overview of Arc-enabled Kubernetes, as well as the Azure services it enables on top. We'll be covering the overview via this deck, but we'll segue into a demo and showcase some of these capabilities directly as well. So let's get started. Arc-enabled Kubernetes allows you to connect, manage, and operate Kubernetes clusters and applications running anywhere, on-prem, edge, or other clouds. It works with any CNCF certified K8s distro and is also explicitly validated on some of the industry-leading offerings such as OpenShift, Tanzu Kubernetes Grid, Rancher Kubernetes Engine, etc. Connecting your cluster to Azure Arc provides an ARM representation of your cluster on Azure, which in turn provides inventory for your clusters. Arc-enabled Kubernetes also provides a consistent way to apply source control and baseline Kubernetes configurations using GitOps. It also provides monitoring and observability experience by extending Azure Monitor services across all of your clusters. Finally, it provides governance and security using built-in Azure policies. There are a multitude of built-in policies available, such as preventing privileged pods from running, pulling images from specific registries, and so on. For the purposes of the demo, I have created 3 AKS clusters that are deployed on Azure, but these can be any clusters, on-prem, edge, or another cloud. Jumping to the script, I have the kube configs of each of those clusters and you can see that the cluster is up and running. I can now run the azconnected k8s command and pass in the name and the resource group of the connected cluster. Doing so deploys the required Arc agents in the Azure Arc namespace and also creates the connected cluster ARM resource. Now this typically takes a while, but after it's done, you can see that the set of agents have been deployed in the Azure Arc namespace. I will now repeat the same process for the other 2 clusters and create Arc-connected clusters for them as well. We can now see that the connected cluster resources are showing up on Azure. The resource itself offers a familiar view to all Azure resources with details like resource group and subscription, and cluster details like K8s version, distro type, agent version, and connectivity status. Before we jump into the GitOps demo, let's look at the flow. GitOps is a cloud-native continuous deployment technique. You deploy an operator within the K8s cluster, and it will monitor a Git or a Helm repository for manifest files or charts. Every time there's a commit or a push to the Helm repository, the GitOps operator automatically pulls the modified resources and applies them on the cluster. It's a declarative way of deployment and ensures that your cluster is always in sync with the state of the manifest files or the Helm charts. If there's any drift in the cluster, then the GitOps operator will automatically reconcile. This is one of the big advantages of GitOps over traditional CD. CD is point in time, whereas GitOps provides self-healing and reconciliation. Arc uses Flux, which is a CNCF incubated project, as its GitOps operator. Arc allows you to create source control configurations, which is an ARM abstraction over Flux. Since there's an ARM resource under your connected cluster, you can create these configurations using Azure Portal, CLI, and ARM APIs. The best part is that you can automate GitOps over all your connected clusters in one click using Azure Policy. Now let's try this on our connected cluster. I'm using the azk8s configuration command, which takes in a few parameters, including reference to the connected cluster, the Git repository URL, and the scope. These configurations can either be cluster or namespace scoped. For this example, I'm using a public repository, but we also support authentication to private repos via SSH or HTTPS. Once the configuration is applied, you can see that the new namespaces have been created within the cluster. These resources were created thanks to the manifest files present in the GitHub repository. Now this is good stuff, But what happens when I have 100 clusters across all of which I want to apply these configurations? It'll become tedious if I have to do it individually for each one. This is where Azure Policy kicks in. You can apply the source control configuration via policy across all your clusters present in a resource group or a subscription. In the resource group, I go to the Policy tab. I click on Assign Policy, and I can see that the scope has already been set to my resource group. For the policy definition, I search for GitOps and choose the one with no secrets, since we're using a public repository. I then go to the Parameters tab and provide the same set of parameters I did via the CLI a few moments back. With that done, I go ahead and create the policy. After the policy is applied, you can see that the resources get created on the other clusters as well. Now, this is not just limited to our current clusters. Any new cluster added within the scope of the policy will automatically become compliant. A lot of the features we talked about in monitoring and governance are actually Arc-enabled Azure services that are extended to your Arc-connected clusters using cluster extensions. You can manage CRUD operations of cluster extensions using Azure and its suite of tools via the portal, CLI, and ARM. First up, we have Azure Monitor. This is a managed observability and monitoring solution that collects metrics and application logs from your clusters and pushes them to a log analytics workspace in your subscription. Since it's a managed solution, you don't need to handle the workspace creation and data persistence. You're also provided an out-of-the-box dashboard to visualize this data. Azure Monitor just became generally available. Next, we have Azure Defender. This provides threat detection across all of your clusters. These threats and vulnerabilities are then bubbled up in Azure Security Center as recommendations that you can look at and remediate. Moving on, we have Open Service Mesh. This is a cloud-native service mesh that Microsoft built and is now part of the CNCF project. It's compatible with the Service Mesh interface and is a lightweight and extensible offering. You can deploy this to encrypt traffic between your services, get service communication telemetry, apply traffic policies, and traffic splits. I'm using the easy KTS extension command to create the Azure Monitor extension. I pass the reference to our connected cluster, and the command automatically creates a log analytics workspace underneath. Once that's done, in the connected cluster resource, I can navigate to the Insights view to see the data sent by Azure Monitor from the cluster. Here, you'll see out-of-the-box dashboards of critical metrics such as node CPU and memory utilization. You also see the list of nodes, the pods, and the containers, along with their performance and uptime. Additionally, you also get a bunch of built-in reports, such as this one. I can see the status of all my deployments directly from here. I can also create my own set of reports. You get all of this out of the box across all of your clusters on-prem, on the edge, or deployed on other clouds. Before moving to the next set of cluster extensions, let's cover some more platform features which will be used to power them. The Kubernetes native way of defining authorization checks involves creation of cluster role bindings and role binding objects in the cluster. The AD RBAC feature instead allows for usage of Azure role assignments as a single source of truth for all authorization checks happening on the cluster. Any request sent to the API server of the cluster is checked with the Azure Authorization Service to see if the entity making the request, be it a user or service principal, is allowed to access the resource of concern. This feature allows for a single place of audit on all the role assignments made on any resource within any of the Arc-enabled Kubernetes clusters. Cluster Connect provides connectivity to the API server of an Arc cluster without requiring any additional inbound communications to be enabled. This is achieved by mapping a hybrid connections resource on the Azure service side to every Arc-enabled Kubernetes cluster where a reverse proxy agent is able to securely initiate a session with the hybrid connections in an outbound manner. This feature allows your developers to access clusters from anywhere for interactive development and debugging. If you already have a lot of investments in terms of paid pipeline concurrency for Azure pipelines or GitHub Actions or any other hosted CI/CD provider, you can now reuse the same to deploy against even on-prem clusters without requiring self-hosted agents on premises. Now coming to custom locations. In Azure, every resource is created in a specific location such as East US or West Europe. This location maps to an Azure region. Custom location allows for the extension of this concept beyond the boundaries of Azure to allow customers to define their own Kubernetes clusters, be it on-prem or on another cloud, as targets for running Azure workload services such as app services and data services. Custom location uses AAD RBAC to create role bindings and cluster role bindings required by these Azure workload services internally. Let's see the Cluster Connect feature in action. After enabling the feature on the connected cluster, I choose to use a service account as the authentication method for the hybrid connection to talk to the API server. I then run the az-connected-kate as proxy command. This command pulls a kubeconfig file that is pointing to the hybrid connection resource on Azure. Now any request sent to the hybrid connection resource will be pulled by the reverse proxy agent sitting in the cluster, which in turn forwards the request to the API server without having to open any new inbound ports on the firewall. Cluster Connect is a crucial part of the platform and powers other features such as cluster extensions. Azure Arc makes it possible to run Azure Data Services on premises, at the edge, and in public clouds using Kubernetes and the infrastructure of your choice. Currently, it supports running SQL-managed instances and PostgreSQL hyperscale. You also get automated updates and evergreen SQL with no end of support. You can elastically scale your SQL MI or Postgres instances with built-in high availability and backup. All of this using familiar tools such as Azure Portal, CLI, and Azure Data Studio. Data Services is also now generally available. Arc-enabled Data Services provides you the option to connect to Azure in two different connectivity modes, directly and indirectly connected. Depending on the connectivity mode that is chosen, some functionality of Arc-enabled Data Services may or may not be available. Primarily, if you use directly connected mode, then you can use ARM APIs, the Azure CLI, and the Azure Portal to operate the Arc Data Services, similar to other cluster extensions. You can view the public documentation page for further details of connectivity mode. For our demo, we'll be deploying data services in directly connected mode. To deploy data services such as SQL managed instance, we first need to create a data controller on the cluster. This involves three things: installing the data services extension, creating a custom location, then deploying the data controller. These can be accomplished directly from the Azure portal. In my connected cluster, I go to the Extensions tab and choose the Azure Arc Data Controller option. Here, we'll need to provide a few things: the data controller name, a custom location. We'll create a new one, and this maps to a namespace in the Kubernetes cluster. We need to provide the Kubernetes configuration, and in our case, we'll select the AKS default storage one. Finally, we need to provide the metrics and log dashboard credentials. In the additional settings page, you can choose to enable automatic upload of metrics and logs. In the tags page, you can provide physical location tags. After all, the custom location is meant to be a representation of an actual physical location of your choice. Now I can create my data controller. Once it's deployed, you'll see the data controller resource on the portal. Within the data controller, you'll see details like the backing custom location, the Kubernetes namespace, the connectivity mode, and status. Jumping into the command line, we can see that the data controller resources have been deployed on the cluster. With the data controller created, we can now create the SQL managed instance. In the portal, I search for SQL managed instance Azure Arc and then click create. I'll need to provide a few details over here. The instance name. I'll need to select a custom location. For the service type, I'll select a load balancer. And obviously I need to provide the SQL admin account details. Once this is done, I can click review and create the SQL managed instance resource. After it's created, you can view the SQL managed instance resource on Azure. Here you can see the external endpoint has been created. You can now connect to the instance using tools such as Azure Data Studio, SQL Server Management Studio, or even the SQL CMD command. Similar to data services, you can now run app services, functions, and logic apps along with API management and event grid on Arc-enabled Kubernetes clusters. You'll need to set up your cluster to become a target for deployment via custom locations, but after that, application developers can deploy these services directly to the Kubernetes cluster the way they deployed to any Azure region. Finally, we have Arc-enabled machine learning. This is another cluster extension that extends Azure ML to your Kubernetes cluster sitting anywhere on premises, edge, or cloud. This allows you to train, inference, and manage ML models on your Arc-connected clusters and build these models closer to where your data lives. With that, we have covered the overview of Arc-enabled Kubernetes and the services on top.
Welcome to the demo. I'm Omkar Kulkarni, a PM at the Arc-enabled Kubernetes team. And let's look at the architecture for our demo application. We have our guestbook application that we are all familiar with, which is a two-tiered application on PHP and Redis. This is deployed across three clusters: Azure Kubernetes Service, Tanzu Kubernetes, and Rancher Kubernetes. DNS helps us identify the load balancer IP addresses, and each application in the cluster is fronted by their own individual load balancer. The database used here is Redis, which is in leader and follower mode, and both have their individual services. Through this demo, we would like to show how the application can be deployed and scaled across clusters using GitOps policy while still pointing to the same database. If we look at the Arc demo hybrid resource group, we would see that the clusters are available to us. And if we move to Arc dashboard, we would see that they are listed there as well. The application code is stored at GitHub. You would see that the code for both Guestbook and Redis application are here. We are leveraging GitHub Actions to perform our CI/CD, in which we perform various actions such as updating parameterized data within the application code, containerizing the application, performing container scanning, and finally pushing the container image to container registry. In this case, we are using Azure Container Registry. We store the secrets used in the pipeline in GitHub secrets under repository secrets and use them in the CI/CD pipeline as needed. If we look at our pipeline, we would see that we have successfully completed a build. In ideal scenario, you would perform both CI and CD as part of single workflow. But in this case, we are storing the end artifact of Kubernetes file in separate repository. These are the updated Kubernetes YAML files for both Guestbook and Redis. If we take a look at our terminal, we would see that Redis database has already been deployed and the service is exposed. In ideal scenario, we would have this Redis exposed internally using internal load balancer or a node port for private connectivity. We would also see that there is no front-end application deployed in the Azure Kubernetes Service, Tanzu, or Rancher Kubernetes cluster. We now take a look at applying policy at scale at resource group level. We go to the resource group, we select policy and policy definition within that. We search for GitOps policy with no secrets as this is public repository. We select assign and we make an appropriate selection for subscription and resource group at which we would like to apply this policy. We click next and we give the configuration an appropriate name and choose in which namespace we would like for this operator to be deployed in. We choose the operator scope to be cluster and we get the repository URL from GitHub. We fill the appropriate parameters such as GitHub branch pointing to main and limit the scope of deployment to just guestbook application by providing GitHub path. We now make an appropriate selection for remediation task and click next. We review our GitOps configuration and ensure that appropriate parameters are filled. We now assign the policy and wait for it to be applied on the resource group within the subscription. Initially, we would notice that the configuration is in non-compliant state, and this is because no front-end applications have been deployed yet. As the remediation kicks in, we would see that the front-end applications would be deployed across clusters. As the remediation task kicks in, we would see that the front-end application is now deployed in the AKS cluster, the TKG cluster, and the Rancher cluster. As the deployment completes, we would notice that we have moved into a compliant state. Let's open a browser tab and open our guestbook application using the DNS available to us. We would notice that the guestbook application is up and running. Let's type in a message and store this into our Redis database. Let's just say, hi from Omkar and Anirudh. Let's make a live change to our guestbook application and edit the heading. Let's add that this is a demo for Azure Arc. Once we commit the changes, we would notice that the application pipeline is kicked in, and it is going to go through the necessary steps defined as per the CI/CD pipeline. We would see that the application redeployment has begun and has been redeployed in the AKS cluster as per the Kubernetes YML file defined. Similarly, we would see that the application has been rolled out to both the TKG cluster and the Rancher cluster as per the Kubernetes YML file. If we go back to our browser and refresh the page, we would notice that the headline for the guestbook application is updated. It now says guestbook demo for Azure Arc. We can also see that the data has persisted for the application. This concludes our demo. We would appreciate if you reach out to us for any feedback related to our product and would like to share any interesting use cases and success stories that you have achieved using this product. Thank you for watching our demo. See you around.